All right, Calculus 2. If we move into section 9.7, what we do, it's called 9.7 Taylor and Maclaurin Polynomials. And we start with this introductory idea I want to try to outline here with you. The idea is we've got this function e to the x. Here's a picture of it, e to the x. And we want to try to find a polynomial that matches or approximates this function. A polynomial that approximates or matches this function. So we could pick any degree polynomial, but I wanted a third degree polynomial. So here's a third, that's the little subscript 3. This is a third degree polynomial, ax cubed, bx squared, cx plus d in general. And so my goal is to find this third degree polynomial, which means find a, b, c, and d. Now I want it to match this function, and what I do is I pick a center point. I want it to match this function centered around what we call c equals 0. Or x at x equals 0. We'll refer to it in the future as c equals 0, the center point. So I'm trying to center it at x equals 0. So here's what I want to happen. I want the function, e to the x, and the polynomial to match at that point x equals 0. In other words, I want them to touch at that point x equals 0. Not only do I want that to happen, I want the derivative, which is e to the x, to match the derivative at, I want the slopes to match up. I want the derivative to match at x equals 0. Not only that, I want the second derivatives to match at x equals 0. And the third derivatives to match at x equals 0. So I took this function and I took his derivatives, which you know is easy. And then I took this polynomial and took his derivatives, 3ax squared, 2bx plus c. The d is a number that goes to 0. Take this derivative, 6ax, 2b. Take this derivative, 6a. And then at x equals 0, I want to equate these. So at x equals 0, e to the 0 is a 1. When I plug this 0 in here, the third degree polynomial, that's a 0 and a 0, I get d. So guess what I just discovered? D is 1. Circle that, hang on to it. At the first derivative at x equals 0, that's also a 1. At x equals 0, the first derivative of the polynomial is c. I just discovered c is 1. Plug in 0 to the second derivative, you get 1. Plug in 0 to the polynomial's second derivative, and you get 2b. Just a little algebra, and you realize that b is 1/2. Finally, the third derivative at x equals 0 is a 1. The third derivative of the polynomial is 6a. When you try to plug in a 0, there's no x to plug it into. You just get 6a, but you can quickly find a. A is 1/6. So we have found the polynomial that best matches this function with these ideas. These are the ideas behind Taylor and Maclaurin polynomials. Here it is. I'll just write it out here for you. Sorry. The function is e to the x. What I just found is the polynomial, third degree polynomial, and a is a 1/6 x cubed, 1/2 x squared, that was my b, 1x, that was my c was 1, and d was 1. So there it is. What's fun is to pick up a graphing calculator and graph this polynomial and watch it match this function. You should graph both the original function and the polynomial. What we say is that that polynomial is an approximation of the function. So this polynomial is an approximation of the function. When you do pick up your graphing calculator, that cubic polynomial, you know the shape of it, it comes up here. And so it doesn't match well here at all, but when it gets close to 0, it matches. Remember, it's centered at 0. So when it gets close to 0, it starts to match. I mean, it's darn close right here. Right at 0, we made it touch. It actually goes through that point. We made that happen. But it hugs the function. It stays with it for a little while. That e to the x function is steeper than this polynomial, so the polynomial starts to fade away. They get off on different trajectories there. But for a while, right around 0, it's a very good approximation. Now the idea is, how could you make it a better approximation? Do a higher degree polynomial. Let's do a 4th degree polynomial. Let's do a 5th degree polynomial. Let's do a 17th degree polynomial. We can make it a much better approximation, and it'll be centered at 0, but it'll hug the function a little longer. Again, it won't be perfect forever. Now you may say, didn't we just get done studying series in chapter 9? What does this have to do with series? These are polynomials. Well, look, these polynomials are a bunch of things, a bunch of terms added together. That's what a polynomial is, and I just got done telling you, maybe we want a 17th degree polynomial. What would make it better than that? A 19th degree polynomial, a 20th degree polynomial. What about an infinite degree polynomial? I think that would be a series. So now I'm taking a big leap here, but I'm trying to make the connection to series. You know, there is a pattern to this. The pattern to this is x to the n over n factorial. And when I do this from n equals 0 to infinity, I've created what's called a power series. It has a variable x in there. You could start plugging in 0, 1, 2, 3. If you plugged in 0, 1, 2, and 3, you'd have this 3rd degree polynomial. If you plugged in 4, 5, 6, you'd have a higher degree polynomial. If you actually went to infinity, you have what we call a Taylor series. Now, again, I just took a leap from 9, 7 up to 9, 10 in a way. Because that's where we talk about Taylor series. But that's okay. I wanted you to see the connection. I wanted you to understand the connection. Why are we messing with these polynomials all of a sudden? If you do higher and higher degree polynomials, an infinite degree polynomial, that's a series. That's called a power series with this variable x in here. And watch what I do now. Instead of calling this approximately equal to my function e to the x, this is e to the x. This is e to the x. Again, we'll get there. This is a nice introduction to find this polynomial. The truth is, after doing this, I haven't really mentioned the Taylor formula and Maclaurin formula yet. So that comes next, and that's kind of really how you do these problems. You can do this for sines, cosines, natural logs. You can take any of these functions and rewrite them as polynomials, approximate them with polynomials. It's awesome. Stay tuned.